Hello everyone, welcome to the channel. Today we are going to discuss about how the distillation columns are designed. So basically till now we have seen the simulation of distillation column, which is very fair close to the design of the distillation column, where you try to separate out the mixture. But you have seen when I was doing the distillation column simulations also, I was expecting like I will start with the eight number of stages with this reflux ratio, or I am gonna start with this reflux ratio. I have predetermined those reflux ratio, number of stages. So how this is decided, we are today gonna learn it. And this is very important for you to know if you are applying for any chemical engineering job, because these kind of things are asked in the interview. So today our topic is to learn the design of the distillation column. So if you know, there are many methods to design a distillation column. So in today's video, I am going to talk about the McCabe, which is the most common, I will say, or the one which you will learn in your college also, McCabe method. In this method, the concept to design a distillation column is very simple. We figure out the operating line. We use the liquid vapor diagram. We find out the operating line of the distillation column, and then we use some geometric techniques to figure out the number of stages, minimum reflux ratio, and the minimum. After finding the minimum reflux ratio, then we go to the operating reflux ratio, that which we are going to design our distillation column. And then we decide its reflux ratio, number of stages, and that is pretty much quite. When you figure out these two number, you are also gonna know about your duties of the reboiler and the duties of the condenser. So let's start with the problem statement. Let's say you are designing this for a company, or let's say you have given a solution A plus B, mixture of A and B. You want to separate it. So what data is given to you? You have know the feed flow rate of A plus B, that is F, and you also know the XA, which you know the XB also, 1 minus XA equal to XB. So from now, when I say X, this means the liquid state mole fraction of A, and Y is vapor phase mole fraction of A. So when you know the mole fraction of A in vapor or mole fraction of A in the liquid, you same time know the mole fraction of B also, which is 1 minus XA and 1 minus YB in the both the states. And I know at what rate I need to produce distillate. That is the distillate flow rate. I also know that is D, because there is a requirement. I want to produce this mixture at a flow rate of this one, or that much amount I want, and you can assign a number also, which automatically decide your bottom flow rate. And the purity of the component A. I am this time I am assuming A is more volatile than B. This is also given, or you will figure it out. Is more volatile than B. This is also given to you. So this is basically the mole fraction of A in the distillate. I am gonna call it at XD. Whenever I am mentioning X, this is the mole fraction of A only. And then I automatically will come to know the about the B. So this is the information given, and the I also know the Y versus X plot for A and B at different temperatures. So basically what I am saying, this is like this. This is Y, this is X, which is basically X. This is XB. So when they, sorry, this is X, Y, A, not X. So when there is no mole fraction of A in the mixture, it is a pure B. And when there is no, when it is basically from 0 to 1. When we are at this point, it says we have only the A left in the A mole fraction become 1. It means there is no B in the mixture. So this diagram is something look like this in for the most of the liquids, I will say. And whenever there is a change in this diagram from the usual diagrams, we will discuss about the case how to design the distillation column in those scenarios. So this diagram is also given to me. So this is all the data what is given to me. Now what I will do, I will design a distillation column. So for design a distillation column, let me draw the first diagram of distillation column, because now we are going to understand about some basics of distillation column. So now this is my distillation column. Now if you see a distillation column, in the distillation column, here I am taking the heat out, and this is my distillate. Let's say this is my feed flow rate F, and this is my bottoms product B. Here I have the mole fraction of A in the distillate. Here is the mole fraction of A in the bottom product, and here is the mole fraction of A in the XF and YF. Why I say YF? Because when you know the XF, you need automatically know the YF by the liquid diagram. It's like in the feed, I know you can figure out the mole fraction of X in liquid and in the vapor phase, but overall for a mixture, I am taking it as a XF. So here, what XF means? Let's say I have a 50% liquid and 50% vapor feed, then the overall mixture means, let's say if I have a 10 moles in the both liquid and 10 moles of A and 5 moles of B, both liquid and vapor phase, then it is just 10 or 10 by 50, basically the total mole flow at that time. So, and B, I am considering complete condensation. My condensation is perfect. So I will have a bottoms product here, and I also had a top product as a liquid. So I have XD and X. So when I do first, simply I know the B because I know the F. So if I go for a mass balance on the whole distillation column, so the simple mass balance will give me B plus D equal to F. So which implies that B equal to F minus D. So I know these things. And FXF, the mole fraction of A, DXD plus BXP. This is also very, I know it very well, because this is what I should, this is just become from the simply mass balance, simple the mole balance of the A, mole balance of the component A. So this is the equation 1, this is the equation 2. We might require these equations. So now what I will do, I will now let you know how to draw the operating lines. So why we need to know about the operating lines? Why McCabe think of operating line? Because I am gonna use the geometric method to figure out the number of stages. So in that scenario, I need to plot. I need to plot my operating line. I need to plot my column on the Y liquid on a chart paper where I already drawn the liquid vapor equilibrium diagram of the mixture of A plus B. So in that scenario, what I need to do, I need to find the operating equation that the vapor and the liquid that are flowing through the column will follow when they are passing through the column, how the mole fraction in the liquid state will relate to the mole fraction in the vapor state. That is what I want to know, and that the relation of liquid mole fraction at a stage to liquid mo sorry vapor mole fraction at stage is called operating. So please be with me. I will explain you. So now let's focus on what I was taking. Let's focus on the one of the section of the distillation column. Let's say I am focusing on the nth stage. Here I have n plus 1. Here I have a n minus 1. So what will happen in the distillation column? From this stage, I will have liquid, because on this stage what is happening, the liquid that is coming from the condenser, here this liquid is gonna fall, so this liquid is gonna make to the bottom. So from the minus 1 stage, I have some liquid that is gonna fall on the l n minus 1 xn on the stage number n, and there is some vapor that is going from this stage, that will be vn minus 1, and it has a mole fraction of component a as a n minus 1 in the vapor phase. Okay, till now what I can assume, at every stage the efficiency is 100%, means there is a maintain the stages are maintaining the equilibrium, the yn minus 1 and xn is in the equilibrium. Now similarly from nth stage, I has a v n plus 1, n plus 1 stage and yn plus 1 going to the stage n, and from the nth we also have the vapor vn, and vn yn is going to the n minus 1 stage, and similarly ln, and xn is going to the nth plus 1 stage. So when you consider the nth stage only, you have vn yn going, ln xn going down, then yn plus 1 is coming, and l n minus 1 xn minus 1 is falling to the column. So this is how overall things are look like. So when I talk about operating line, as I am saying the efficiency is 100%, so these points are on the equilibrium line. So what I am gonna try to relate, the operating lines means how these 2 points are related, how these 2 points are related, or how these 2 points are related. What operating line means, on a stage, if I consider the bottom section of the stage, how these 2 points will be related or how these 2 points will be related, because these 2 points are in a equilibrium. So if any stage I know the relation between these two, I can easily find the this relation, and vice versa, I can predict what is happening on the one stage or at the down stage. So in that scenario, I can draw the whole distillation column, or I can predict the whole distillation column. So now what I will choose? I will choose to find the relation between ln and yn plus 1. Sorry, xn and yn plus 1. That if I am before going forward to figure out this thing, what I will do, I will make another terminological term that you should know, because this is generally used. So when I am talking about distillation column, sorry, this way, this way, this way, and yes, vapor is, this is the distillate, this is the bottom product, this is the feed. So this part is called the rectification section, and this part is called the stripping section. So now let's start the find out the operating line for the rectifying section. Let's start the rectifying section operating line. So we will gonna find these by just the virtue of mass balance and the mole balance, mole overall mole balance. So now this is my problem statement. Let's change the page so that we are starting very fresh. I am liking to start afresh. So operating line of rectifying section. Let's draw the rectification section. So by now you have on the nth stage I am drawing. So this is the my system that I considering for mass balance. This is the nth stage. I told you it has a yn plus 1 and vn plus 1 coming in, ln plus 1, ln and xn going down, and there is a condenser. So from now we know condenser is a zeroth stage. So I can name it as a the liquid that is going from it as a L0 X0, which is basically the XD, because here the liquid is divided in two part at the condenser. So that's why, sorry, this is the rectification part only of the distillation column. So that is why, because XD and X0 will be same. So this X0 is equal to XD. And here I have a vapor that is coming from the first stage. Because condenser I name as a zeroth stage. This is the first stage. Because at condenser, there when we are condensing something, there is a still a liquid vapor equilibrium stabilized, because we are condensing the things which is basically equilibrium thing. That's why this is considered as the zeroth stage when we have 100% condensation. So I'm assuming the 100% condensation here. In other case also, we have a equilibrium stabilized between the vapor and liquid, how much heat we are supplying. So in that scenario, the this is a one of the stage of a distillation column, so it is considered as a zeroth stage. This is how the terminology works. So this is will be the v1 and y1 that is coming from this stage. The vapor coming from this stage is condensed. Now what we are gonna do, now, we are gonna stabilize some relation between these things. So now you will see there is a vapor flow in the column from bottom to top. There is a vapor that is vn, then vn minus 1, then vn minus 2, and so on is going on. And there is a liquid flow that is the L0, L1, L2, L3, L flow from bottom to top. So there is an assumption that McCabe is taken that the liquid mass flow rate throughout the column is constant, and second, vapor mass flow rate throughout the column is constant. Now you will see why he choose these two assumptions. How he is too sure about these. So let's say it is not constant. There is a continuous change in the liquid mass flow rate from one section to another section. So when there is, so what will happen if there liquid, as it is coming from top to bottom, its flow rate is reducing. In that scenario, the column will not work at its uh, actual efficiency, because when the liquid is coming, the amount of liquid is going down. At those points, there will not be much stripping that is going to happen, and then the vapor will not be saturated. Then we require a very large column. So you assume that the column that are working fine, this condition should met, or otherwise you can also think why there will be a change in the liquid flow rate from L1 to L2, because there is some amount of vapor that is going to let me explain you with the diagrams. So let's say these are the two stages I am talking about, that n minus 1 and nth stage. From here, that there is a liquid fraction L, xn coming, xn minus 1, ln minus 1. Here is a ln, xn. So I say ln minus 1 minus L is not equal to 0, ln. There is a some change. So why this changes happen? When ln minus 1 is gonna come to this stage, what will happen? And there is also a vn minus 1, vn plus 1 that is coming, and there is a vn that is going on. So this ln minus 1 when come to this stage, some amount of it is gonna be go to the vapor phase by virtue of heat. And similarly, vn plus 1 Vn plus 1 is gonna reduce some amount of its vapor to the liquid phase. So there is a transfer from liquid to vapor because this when we going in the distillation column. So when I take the more volatile component at the top, so it is close to the boiling point of the most volatile component, and it is the bottom is close to the temperature of the boiling point of the, let's say this will be close to the T temperature A, boiling point of A, and this will be close to the boiling point of B. As A is more volatile, so the temperature in the column is increasing as we move downward. So the temperature TA will be greater than TB. Similarly, the temperature as N minus 1 stays at temperature N, Tn is greater than Tn minus 1. And Tn minus 1, the temperature Tn plus 1 is greater. So when this vapor is coming to this state, its temperature is going to reduce. It is going to lose some of its vapor to the liquid Ln, and similarly this liquid, as its temperature going to increase, some of its liquid is converted to the Vn, converted to the vapor phase, which is going to add the vapor mole fraction of n. Now let's say this amount is m1, this amount is m2. Mass transfer that happens is m1 and m2. Well, m1 is equal to m2. When m1 will be equal to m2, m1 will be equal to m2 in two scenarios: when the temperature profiles, or I will say when the, if you take in very vague terms, if let's say the heat, latent heat of vaporization qa is very similar to qb. In that scenario what will happen, uh, in that scenario what will happen, whatever the mole fraction of xn and x, whatever will be the mole fraction xn or xn minus 1, there will not, they are not similar, but the overall latent heat of vaporization of that mixture at any stage will be same. So whatever amount is lost, whatever amount of heat q2 that is lost when the Vn plus 1 is condensed to the liquid L, condense and add some part to the liquid Ln, the same amount of heat will gonna make vaporize same amount of vapor L from the Ln minus 1, which will add to the Vn. So whatever amount Vn plus 1 is lost, the same amount is gained by the Vn. So so in that scenario, Ln minus 1 is equal to Ln minus 1 is equal to L. Why? Because whatever Ln minus 1 is loose, the liquid flow, the same amount is gonna taken by the L. So the amount that the liquid is lost is gaining when Vn plus 1 is reaching the stage. So the amount of liquid, if I just consider the liquid phase, so Ln minus 1, there is some Q is taken, there is some M1 is taken, then M2 is added, but m1 equal to m2, these two are gonna cancel and it will become equal to ln, and so on. So what will happen, ln minus 1 is equal to ln equal to l0 and equal to l. Similarly, if I talk about the vapor phase, so vn plus 1 approaches the nth stage, it loses some mass m2. Then there is an addition of mass m1 in the vapor phase from ln minus 1, which will make vn, but as m1 is equal to m2, both will cancel out and vn equal to vn plus 1, and so on, and it is equal to v1 equal to v. So these are the two logic explanation of this assumption, and it is valid when the latent heat of vaporization of two component is equal. So you need to take this into account, because if you are not taking this assumption into account, or you know not know about this assumption, believe me, many time interviewer asks you to check the depth, the knowledge you hold. So please take care with this assumption. I think it is very, sometimes it will become very difficult to understand it. So it is advisable that you do hands-on when I was also explaining this. So coming back to the operating line, operating line determination part. So let me draw the nth stage and the half of the distillation column. So from the nth stage, only ln is going down, vn vn plus 1 is coming from the bottom stays nth plus 1. There is a vapor V1 equal to V going. There is a here is a condenser, and there is a liquid L1 equal to L coming, and D x1 equal to xt, as I explained you, because both the liquid are separated from the same condenser, so they are the part of the same condenser only. So now let me apply the mass balance here. So when I apply the overall mass balance, D will be equal to, D is the mass that is going out, equal to, sorry, let me apply like this way. Whatever coming in this system, the only thing that is coming in this system is Vn plus 1. Whatever is going out, Ln plus D. This should hold. First thing, this should hold. This is the third equation. And another component balance of the mole, let's say I say mole balance of A, component A. So the Vn plus 1 Yn plus 1 is the mole of A enter this whole system that we are considering, and xd D plus ln xn is the amount of the liquid, that amount of the xa, that amount of the A, moles of the A that is going out. So this should hold true. This is the fourth. Now by assumption, what I can write, V equal to L plus D, V into Yn plus 1, this become the third, and this is the dxd plus lxn. This become the fourth. Now substituting 3 in the fourth, L plus D Yn plus 1 equal to dxd plus lxn. After substituting this into this, now if you follow closely, what I will do, Yn plus 1 equal to d divided by L plus D into xd plus L plus D xn. Now I called it as a one of the ratio that I'm gonna talking about. That is a reflux ratio. So what is a reflux ratio? You also know, R equal to L by D. This is the definition of the reflux ratio, where L is the liquid that is coming to the distillation column, and D is the liquid that is going out of the distillation column, where it basically after the condenser, this is the uh, L is the amount that is coming into the distillation column from the condenser distillate, and D is the amount that is going out. So this ratio is called the reflux ratio, and we represent by the symbol R. So when I substitute this into the above equation, it will become, I divide the whole equation by D. L by D plus 1 xd plus L by D plus 1 xn. Sorry, L. Replace L by D with R. Yn plus 1 equal to 1 upon R plus 1 xd plus R upon R plus 1 xn, and rearranging this in the form I want, Yn plus 1 equal to R plus 1 into xn plus 1 upon R plus 1 xd, which is my fifth equation, and this is the ROL, rectification section, rectifying section, operating line. So this is the rectifying section operating line. Now let me see how this line is gonna be look like on the plot. So we know the slope of this line will be this one. This is the slope, and this is the extra term that is added to it. So we are mostly worrying about the slope. So slope is decided by R plus 1. Now, if you consider the top part, let's say I am considering the zeroth stage, V1, Y1 is coming. Okay. And what? V1 Y1 is going coming, and what I call XD, and XD is going out. So at the zeroth stage, n becomes 0. So you will put y1 equal to r upon r plus 1 x1 plus 1 upon r plus 1 xt, sorry, and x0. But we know the x0 is equal to xt because it is coming out of the same condensed state, and it is the just the same liquid or the same amount of mixture divided into two parts. So in that case the mole fraction is gonna be same because we are just dividing the mass flow rate. We are not gonna do anything with the equilibrium of the mixture. So x0 equal to xt. So by this logic it become xt r r plus 1 plus 1 upon r plus 1, and you see this will become 1, and y1 equal to xt. So this point is lie on the line y equal to x. Why? Because here y1 equal to xt means like the y or the y-axis coordinate of this operating line is same equal to the x-axis coordinate, and which will lie on the 45-degree line. So when I see the when I see the liquid vapor equilibrium chart, you see this is y a, x a, or let's say this is y and x, whatever you want to call. So when I am going to draw it, it's, let's say it is a 45-degree line, which is usually a 45-degree line because it is going from one end to the second end. This is a 45-degree line only. So this is the line y equal to x. So my y1 x1 gonna lie here, and this line will have a slope of r plus 1, slope of r plus 1. Yes, it has a slope of r divided by r plus 1. So this is the operating line. So I have drawn the first operating line. Now I need to figure out the second operating line. Then I will have my distillation column on the chart, and after that, once I have my distillation column, then after that I will let you know how to figure out the number of stages, minimum reflux ratio, and the operating reflux ratio. So this is how the McCabe works. So for now we have just figured out the uh, what we have figured out the operating line of the rectification section. So you just revise this tutorial, and every concept I have taught you just do by yourself so that you are very versed with it, because you need to be very clear with these concepts. Otherwise, in most of the chemical engineering interviews or your exams, you might be confused when some problem is given to you. So thanks. Let's wait for the second video in which I will explain the how to determine the feed conditions and the operating line of the stripping section, and then the other process and the other parameters, how to determine those when we decide or when we figure out the distillation column design. So thanks for joining. Please like